All right, so welcome everyone, and thank you for paying a little bit of attention to me while you are eating. I hope my talk will provide some additional information. So, what's on the screen is on the upper panel is a simulation, global simulation using our flagship climate model. And lower panel shows the global stationary satellite observation. So you can see they agree with each other reasonably well. And our job continue to be to learn about the nature, how is the nature changing, and how can we and we codify those knowledge and put it into models. So let me put that away. That's just a eye candy for you, and before you. So you have some dessert while you're eating. So I wanted to talk about challenges in Earth science informatics. You notice that I didn't use big data. I didn't put it on my title. For some time, the past couple of years, it has been pretty significant development in big data. There's a lot of big data talks and products and research coming out tremendously. And it's all come all over the place. So a lot of time when I talk to our program managers and my colleagues, and people in domain science a lot of time feel frustrated because their issues and challenges are not addressed. And I wanted to use this one slide to kick off this talk. I took this slide from the internet. It's a IBM slide actually. So it shows the data volume, how quickly the data is being used and transformed. And the reason I use this slide is really just for one. This probably you can't see it. For one data right here, Google is processing 24 petabytes of data a day on the left-hand side. 24 petabytes of data a day. For quite some time, NASA's climate science have been collecting the data. We use satellite observation. We've been collecting satellite observation for many, many years, since 1979. We put those data together, put it in our data center, and we were very proud to say we had one of the biggest data set together, and that's how much, that's only 10 petabytes of data. So for the past more than 20 years, since 79, that's 30 years, 34 years, we had 10 petabytes of data. But today, Google is processing 24 petabytes of data a day, right? So data, how big is the data? It's all relative. And Steve was saying it's all relative. It's about how you process the data. How do you deal with the data? If you can use your past processing system or past methods to process the data, it's big to you. So it's all relative. So I'm very happy that this is the Gartner's hype cycle, that big data, the term big data has passed the peak of the hype cycle, and it's coming down, and now the community, in fact, we are actually dealing with real big data problems now. Okay, so we kind of passed the very noisy state and starting to have a lot of true actions coming out, results coming out. So I used this slide for many years. It's still very true. NASA's work is to process the data we collected and start going from left to right to process data, to clean it, to put it in certain kind of a data system. We extract information and turn those information into knowledge. So the theme of this conference is, symposium is from data to knowledge, right? This is the workflow. This is what we have been doing for many years. And you can see in every step of the way that the data volume start reducing. Through various algorithms, we can extract the information out of the data set, the raw data sets, and turn it into knowledge. This workflow is shown on this slide, and we have we actually built our research program around it. On the left-hand side, we have data input. So we collect the data. We use data from multiple platforms. We start to organizing the data, and then start build programs around it. We turn the observation, and also we understand the observation and codify those knowledge into models, and models collect those, represents knowledge, and we try to predict the future. And that's what the climate model, weather model is doing. Weather model can do, I think Jeff was saying 14 days. Climate model typically project out to 100 years. We don't use prediction in climate. We say projection, right? It's a probability. So we collect the data, and we turn the knowledge into models, and we use that to do prediction, and the prediction can feed into policy and management decisions. And this morning we see the talk right before lunch. John Deere is using a lot of the information for precision agriculture, to increase crop yields. So this is also a chart. This is also a chart used for many, many years that basically describes our data system. Left-hand side, there's a data acquisition process from satellite, from airborne platforms or in situ observations. We start to collect those data and put it in a platform, clean the data, prepare the data, and start moving the data set to our right-hand side. And we build research programs on the right-hand side to analyze the data. Maybe, let me see. Right. So those are the programs we call AXIS, AIST, CMAC, and Measure. Access is the one to provide higher level data access. AIST and CMAC deal with the computer science type of issue, the infrastructure issues. How do we develop the algorithm to interrogate the data? And Measure is another program to clean the data set, clean the high-level data set to extract some information out of putting together higher-level data products. Okay, those are our traditional program. And you will notice on this chart that the users is on the extreme right-hand side. It takes a very little room on this chart. This was our traditional focus. Our traditional focus was on data processing. I guess my knowledge is, data processing has its own workflow, has its own emphasis, and I will talk about this a little bit. So, in the scientific research, NASA is providing the data and information to our scientists, and you will notice that the workflow is basically they often use computing services to perform data analysis, theory verification, and predictions, right? And when they do that in the past, they often FTP, go to some server and fetch some data to your own labs. And I used to show a chart from Ian Foster at Argonne University. Basically, each faculty has his own lab and has basically a small cluster or workstation, and they can put some data in their lab and do the data analysis. That model is becoming more and more impractical because data volume becomes bigger and the problems we are attacking is bigger. In the past, it's more local, and now we are turning global. Right? We are tackling bigger and bigger problems. Okay, so that model is becoming very challenging. And I just talked about this workflow. So typically, what they need to do is to go to a data center to find the data set. Find the data set and then identify the data set, place an order, take the data back. So think about every step of the way that some service, some of the additional work that needs to be prepared and put it in a database so you can, the scientists and engineers can use that kind of service to get to what they want, right? And data is transmitted to the home institution, put it on local servers for the analysis. And this is exactly the problem that the old paradigm is, kind of broken in the big data era. I often say this is a kind of a traditional library science. What you're doing is, the problems they are focusing still is a data creation, indexing, cataloging, searching. How do you search the data? And of course, to provide certain services to the user. How do we provide ordering, subsetting? Subsetting was important because the network bandwidth is not big enough, so you cannot bring back terabytes or petabytes of data to your home lab. Okay, so this is the type of workflow and the services, functions that we focus on. By the way, this is still existing. This is not going away. Big data is additional work. It's beyond the traditional work, right? And this is $200 million program right there. Okay. So this is continue to be very valid, work that we continue to do, continue to provide. And one thing I wanted to show is this chart. It's a data management challenge. So a lot of time we collected the data and we index and catalog the data and put it in the database. Guess what? We forgot about that. People can't find it. People don't know about this data set. We collected 10 petabytes, but only a small portion of data are widely used. So if you look at this chart, a lot of time you still need experts who collected the data or who's working on the science team, who has knowledge to the data that you have to talk to. And if that person had an accident or died, that data is permanently lost. We rely on expert system, so much. You pick up a phone and call a university, researcher saying, "Oh, I need this data set, and tell me what's in there, what information I can get out of it." We still rely a lot on this kind of expert system, expert knowledge. So we need to do a better job to manage the data. So this morning I was listening to the IBM talk, and I drafted this question. This is really a very, very important question that I've been thinking about. When I learned about Watson a couple years ago, right? I wanted to have a natural language. I wanted to ask a natural language question to Watson. This data set is used for predicting crop yield in a model. I don't care what model it is, right? Put in the words. And under the future climate scenario, certain scenario, you put a natural language to a knowledge management system, an expert system. Watson, which is an expert in this case, will tell you what is temperature and precipitation data set from this place at this data center, and here's a document that you can follow, right? So this is something I wish that I can give to all of my PIs, all of my researchers, so they can easily find the tools and data sets that they need. Okay, and this type of work doesn't come from domain scientists. You can't ask a meteorologist like me to do this kind of work. You need some interdisciplinary team to build this kind of a knowledge system, right? A totally natural language system. You can imagine, in order to do that, Watson will have to consume all the research papers, parse the paper, parse the language. It knows what data set being operated on by certain kind of tools, to answer certain kind of questions, right? So that's possible. I think that's coming up very soon. Watson is now being used for medical applications, and with some additional work, we can do a lot more other things, other fields, right? So use the imagination that it's just this is a data management challenge that I can see that we are facing, and we should solve it in the next couple of years. Well, I have some technical issues. Here we go. So moving on, our observation system continue to evolve. We are taking more and more observations. This is a satellite we just launched a couple months ago, 6 months ago. It's called OCO, Orbiting Carbon Observatory. It's collecting the carbon emission kind of information. So I've been working with the OCO team to figure out how do we go through that process, how much data are we processing, are we talking about. So every day, we are collecting 1 million soundings a day. It's orbiting the Earth, it's collecting data. Sounding is temperature, humidity, not in this case, it's carbon concentration in the vertical atmospheric column. So it's collecting 1 million soundings a day. And we wanted to, in a couple years, in 2 years, we wanted to process that data set, right? So every sounding, today, you wanted to process and turn it into a carbon concentration number. Satellite takes radiation measurements, right? You wanted to turn it into carbon concentration. You need to process the data, turn it into carbon emission. So that's 16 minutes per processor hour. Okay, 16 minutes per processor. You can easily calculate how much computing power and how much data is there using this chart. So this is just one satellite platform, one instrument. And we use that kind of data and put it into this kind of a model. And this is the model I showed you at the very beginning. We call it, it's a global model. Right now it's a global resolution of 7 kilometers per pixel. Okay, so you can see it's pretty realistic right now. And this experiment is used to design our future generation of observation platforms. What kind of instrument, what kind of orbit, what kind of configuration, be it a small satellite or big satellite, what's the repeat cycle, what's the inclination. This is the system to make that kind of a decision, right? And this experiment itself generate 2 petabytes of data for 2 months of weather. Okay, so it's just showing the data volume is getting bigger and bigger. And here's another chart. The projected growth in climate data output. We wanted to know what will happen 10 years down the road or 20 years down the road. Already, Navy is asking NOAA and NASA what's the climate look like, what's the sea level 30 years from now, because they wanted to build shipyards, right? And they are worried about that kind of infrastructure. When we plan infrastructure, we plan 30 years ahead of the time, right? So there's really real consequence there. And a lot of it, we are trying to extract that kind of information from this kind of data set. And this data set shows, I don't know how many climate scientists are here in the audience. We did a climate assessment in 2007 and then 2013. 2007, we had 300 terabytes of data. 2013, we have 2 petabytes of data. And it's projected out, 220, we should have 150, almost 150 petabytes of data. Right? It's growing tremendously. And the blue color shows observation, and the orange color shows the model. So the data set is certainly growing tremendously, and it's going to be a big data management challenge. Did I go too far? I think so. Go back. Now I'm going, here we go. Wrong direction. All right, so gearing up for big data analysis. So we now know our traditional data analytic workflow doesn't work anymore. We start to work toward our future platform. And since 2008, we started looking into how do we move forward to our future platform. We set up the program which started to look into the technology and data management system. And I don't know, how many of you are familiar with NASA's programs? Some of you, yeah. So NASA is very good in building capacity. We start thinking forward, what's needed 10 years down the road, and we start building capacity first. Once we start the capacity, we move on to research analysis program, start awarding additional analysis work, and then move on to transition program that will transition some of the technology, moving some of the technology to industry or to application. So we started working on this platform since 2008 as a kind of a prototype and advanced prototyping of a platform that can be used by climate scientists. We call it NASA Earth Exchange. Using this NASA Exchange, basically we put the computing, the data set, and all the tools all together in one place and start enabling the analysis workload. So we call it climate analytics as a service. Okay, and that's one activity. And then you all know research enterprise, we typically don't put everything in one basket, right? We start diversing a little bit, not too much, because we know models has its own bias. We bring in some of our observation to interrogate the models. That's observation for model intercomparison project. And we use some of the technology. Many of them are not developed at NASA. IROD was built by NSF, SciDB, NSF, and DoD. Hadoop, that's open source, we are using. Hadoop MapReduce. Apache OODT, that's developed at NASA JPL. And now Apache OpenClimate, those are, that's also started at NASA JPL, now it's open source. Why do we do this? Why do we put it in open source? Because funding agency like NASA, we typically has this 3-year funding cycle, and that's too slow. We wanted to put it in the open and make it available to all the researchers, and hopefully we can speed up this development process. And a lot of the research, and especially currently, we focus on how to manage the data movement and movement from the archives to the analytic platform. Because you think about that, the data right now resides in data center, typically in the format that's optimized for data archive. It's not optimized for data analytic workload, right? So we need to think about how we convert those data and how do we move data from the archives to the analytic platform. So if you take a look at this, this chart, this is kind of an architecture diagram. On the left-hand side, that's the traditional library science type of functions. On the right-hand side, that's more of the analytic functions. So we are busy working on the right-hand side, trying to make it more useful. So on the right-hand side, the new challenges are emerging. Those challenges include, of course, data visualization. We talked about that this morning. Server-side processing. You can't move petabytes of data to your own lab anymore. Well, although recently I do have one PI at Illinois. He moved 1 petabyte of data from our atmospheric data center at Langley, that's in Virginia, to Illinois. Of course, NCSA has the biggest supercomputer, right? 1 petabyte of data, no problem. And using the technology, Globus Online technology developed at Argonne. So we focus our research on the server-side processing. Data mining is important, machine learning. We are dealing with large volume of data, so humans, interaction, it should be there, but we think machine should do a lot more work than before. Machine learning, and I will give you an example. One thing that worries, we are very concerned about is distributed data analytics. Data were in data centers, distributed in many cases around the world. So in a sense, you don't have a complete sample at a data center. You have it distributed at different data center. So the statistics you collected at each one of the centers are partial. Okay, So how do we avoid certain kind of bias and not to, very simple ones, counting the numbers and put them together. Those are, you don't make mistakes that way. But some of the more complex statistics may be depending on the sample size. So that's a area that we are very concerned about. I talked about data onboarding, moving from the storage to the analytic platform. ETL is a traditional database kind of term, extract, transform, and load. That's a typical server-size problem. High-speed network, we continue to need high-speed network to move the data to to PI to some of the institutions. Here's so I talked about NEX. NEX is a collaborative platform. As a prototype, we started 2008. It's been a couple of years. It includes supercomputing, data sets, a sandbox for people to play, to try their algorithms, to interrogate the data, right? This morning there was a question, how many people have been trying to get their hands on some big data sets, right? And it was very difficult to get, to experiment on a large data set, and it's not all over the place, right? You have to go to the right place to practice your new algorithm. So this platform provides an opportunity, provides a platform for you to do your experiment. I talked about this, and it's a coupling of computing and data collections, and we built together a environment for people to interrogate the data. Sometimes it works, sometimes it doesn't. Okay, here's one example. We have 20 years of Landsat data set. This morning, I think Jeff showed the Landsat data set on the lower right. You can see the lines between different orbits, different scan, different swaths. On the left-hand side, we actually put the data set together using some of the optimization algorithm, put together the global data set. So once you have the data, large volume of data together with computing platform, you can start doing a lot more things with the data set. This is another example for using 35 climate models, those climate projections. We use statistical downscaling to get down to very high resolution climate data. This data set is 800 meters resolution. So it's very, very high resolution. The product itself is 40 terabytes. And many people, and we started additional program to try to use this data. You can imagine we can apply this kind of data to crop yields model or flooding, all kinds of application. Of course, we can take a look back in time, what kind of change had been there. This is the Landsat data analysis. And we also support data monitoring, carbon monitoring. using multiple platforms and put together data products so we can understand what kind of vegetation, how much carbon we are storing or emitted. This example is also very interesting. In the past, we have an expert system to identify fires, and fires is one of the primary sources for carbon emission. And we now, because we put a data set together, all the data on a platform, we can use multi-year analysis. This is purely unsupervised machine learning and data mining, identify additional areas that was previously unidentified. And it turns out we probably missed 25% of carbon emission in the past. Right? So this is another very interesting work that we are learning from electrical engineers and computer scientists about this mission, miscounted fires. So here's another new project that we are starting is above Science Cloud. We are developing new experiments to measure our boreal forest vulnerability. And because of the high resolution data required for that experiment, we decided once again to put together the data set and the compute platform. In this case, specifically designed for this experiment, we are going to have global high resolution topography at 50 centimeter resolution, 50 centimeter global. Right, that can be used for carbon counting, forestry, and fire, and also water management kind of application. Right, so future direction. I see this is becoming, big data is becoming a core necessity for future science enterprise. We need big data, we need to address this problem, and we see some of the challenges. We need to do server-side processing, we need to access the data, high-speed access, and also we need to thinking about data centers. We are not consolidating all the data centers, so we need to think about the distributed statistical analysis. And of course, cloud is very interesting. How do we make use of this kind of a new cloud platform? And we are thinking to use some of the virtualization technology, develop the virtual machines to use in the cloud. All right, so here's just one chart for some of our research opportunities. And if you have questions, just call me. Thank you. Thank you.